break it apart into all of the different wavelengths of light. There might be all the colors of the rainbow and more, right? Also infrared and ultraviolet and so on. Okay, and what we learned is that the luminosity of some object is proportional to its size, which goes as the square of its radius. Think of a sphere like a star. So the surface area of the star, the square of its radius, and the temperature to the fourth power. So get a star that's larger or higher temperature, more luminous. Stars, we talked about range of luminosity all the way from about a 10,000th of the luminosity of the sun, all the way up to about 1,000,000 times as luminous as the sun. And astronomers don't just use watts to describe the luminosity of the sun. Sometimes they use units of sun, so like twice the luminosity of the sun or 10 times the luminosity of the sun. But other times we use the magnitude scale. So we introduced you to the concept of 5 steps in magnitude. We use an M to represent the luminosity of a star, where 5 steps in magnitude correspond to a change in luminosity by a factor of 100. So you'll sometimes also see that. Okay, so this is one big fact about stars, is how intrinsically bright they are, the luminosity. But remember that we can't actually, when we look at a star, what we actually see is its apparent brightness. Okay? We don't actually know how luminous it is until we determine its distance from us. So we have to tease apart the apparent brightness from its distance, right? If we see a star that looks bright in the night sky, it could be because it's close to us, or it could be really, really far away, but be very, very luminous. So, right, we worked out last time that the apparent brightness goes down as the square of the distance, right? So the star has some luminosity, but if you get twice as far away, you're 4 times less apparently bright. And luckily, we can find the distance to stars, and we've mapped out the distance to about 1 billion stars in our galaxy using what's called stellar parallax. Okay? That is, the Earth moves around the sun, so the Earth is moving. And just as when you're moving, like in a car, you see closer things in your field of view move more in your field of view relative to distant things. The same thing is true of stars, right? So as the Earth moves around the sun by, say, a few months, you expect to see closer stars to have more of a parallax angle. They move more relative to further stars. And the equation we derived last time was that the distance in parsecs, each parsec is about 3 light years, can be calculated as 1 over the parallax angle in arc seconds. So if a star moves in your field of view by 1 arc second, as the sun moves, the Earth moves around the sun, then it's 1 parsec away. Okay, so that's how we figure out the luminosity of stars. And that's going to be one of the 2 really important ingredients when we talk about our HR diagrams. And then the other is the color of stars, right? When we look at a star, we see both its brightness and its color. And remember, we talked about when you put the starlight through a prism, you get its spectrum, and spectra are related to temperature. So hotter things are bluer. Their spectra have all the colors of the rainbow, but have more blue. And cooler things have all the colors of the rainbow, but look more red. Okay. And stars range in general from about 3,000 degrees and look pretty red, up to about 50,000 degrees and look pretty blue. And we talked about how we classify that spectrum, where O is the bluest and hottest surface temperature, M is the lowest surface temperature, the reddest. So I wanted you to memorize O, B, A, F, G, K, M to remember the spectral class of stars. The sun is kind of in the middle. The sun is kind of a yellowish G-type star, but there's M-type stars that are redder, O-type stars that are bluer. And the way astronomers measure this is through the BV color index. That is, you look at a star through a telescope with a blue filter, see what the magnitude is in blue, and compare that to the magnitude in all colors, visual, V for vision. And that way you can tell how blue the star is using that BV color index. So sometimes when we give the color or temperature of a star, we'll alternatively give the BV color index. And here's just an example of O-type stars through M-type stars, their spectra, right? So if you look at an O-type star through a spectrometer, through a prism, you see all the colors of the rainbow, but there's more blue because it's hotter. M-type star is a lot more red because it's cooler. Okay. there any questions, kind of recapping what we talked about last lecture, about ultimately learning these two things that are going to be really important: the luminosity of a star and its temperature. You can probably hear it's really windy outside. I don't know if it's the same for you. All right, no questions about last time. All right, well, let me give a poll question kind of as a warm up. This is a question I asked you last time, so let's make sure that you have a good foundation for what luminosity is. Let me get my poll here. Star luminosity. All right, everybody. The luminosity of a star is the what? Is it the apparent brightness? Is it the surface temperature of a star over its lifetime? Is it the total amount of energy it emits over its lifetime? Or is it the total amount of energy it emits per second? I'll give you about 10 more seconds to plug in your answers. Okay, I'm going to end the poll. And good, yes, so most people got the correct answer. It's the total amount of energy that the star radiates per second, okay? And it looks like the second most popular option was the amount of energy it radiates over its lifetime. At least that's close, that's the basic idea, except remember, luminosity is energy per unit time. How much energy is it? So think of a light bulb, right? A 50-watt light bulb, say, radiates energy per unit time. You know that because the longer you run the light bulb, the more energy it costs, right? So it's emitting some, using some energy per unit time. So the longer the time you use it, the more energy overall accumulates. It's important also to recognize, just for example, the luminosity is related to the apparent brightness, A, but you need to know its distance, right? So we see the apparent brightness of a star, but we have to measure its distance, and then we know its true luminosity. And that'll be really important when we talk about what we're talking about next, which is the HR, or Hertzsprung-Russell diagram. Now, this is the subject, this one diagram is the subject for the whole rest of this lecture, and it's really kind of amazing. It contains a tremendous amount of information. Okay? So we're going to go through it a number of times to make sure you get it. To start, last lecture we learned how you can determine the luminosity of a star, right? How intrinsically bright it is. Well, we can plot that. We plot that on the y-axis of this diagram. So this diagram shows a whole lot of stars. So 1,000 stars that I looked up in a database of stars. And we can plot their luminosity on the y-axis. An alternative to luminosity, remember, is magnitude. So the units for luminosity we're using here are in units of the sun. So this here corresponds to the brightness of the sun. In fact, the sun is shown here in yellow. That's our sun. So either you can think of luminosity in terms of units of the sun, like sun's brightness, or 100 times the brightness of the sun, or 100th of the brightness of the sun. Or you can think of it in terms of magnitude. The sun's absolute magnitude is about magnitude 4. Okay? And then on the x-axis for each of these stars, so all of these points of light, black points is a star. Not only do they have a luminosity, they also have a color, they have a temperature. Okay, and so when we think of a star's color, right, we can think of its color index. So you can either use its color index to plot where it goes on the x-axis, or remember that corresponds to the star's surface temperature, which can be 40,000 degrees Kelvin down to below 3,000 degrees Kelvin. So blue down to red. And remember, another way of categorizing those that's probably used most often when you're talking about stars is the spectral class. Type O is the bluest, type M is the reddest, and the sun here in the middle is a type G. So what we have here is a plot of, if you take all the stars in the sky, you plot their luminosity and you plot their color, in other words, their temperature, this is what you get. By the way, in addition to all the black points, I've just highlighted in blue some of the brightest stars in the sky. So the ones that you see and the ones that make up constellations are the one in blue. You see that they're kind of upper in this diagram, meaning that you see them because they're very luminous. I've also shown in red some of the closest stars. These are harder to see. We might not be the ones that are prominent in the sky, but they're closer to us. But you might not see them because they're not so luminous. You see they're kind of lower in the plot. And that kind of gives a hint to something we'll talk about later, which is that low luminosity stars are most common. Right? If we look near us, we see a lot of low luminosity stars. But high luminosity stars are just easier to see. So we're already beginning to see there's a lot of information contained in the sky. Let's also talk about there's a pattern, right? When we take all these stars, we plot their luminosity versus their temperature, we see a pattern. What is this? So you see that there's this kind of lane of dots going from the upper left to the lower right. Okay, we call this the main sequence. This is where stars spend most of their lives, and this is where they're burning hydrogen through fusion into helium. That's their main energy source. Okay? And what we'll learn is that as these stars die, we'll have a whole couple of lectures on the death of stars. As stars die, they begin to balloon up and become giants. So actually, all of this, so the upper right here are all stars in their dying stages that have exited the main sequence, we say, and they've gotten redder. So you see they're moving to the right, so the redder, but they're getting more luminous. And as we'll see, that's because they're getting bigger, they're becoming giants. And we also see this, what's going on in the lower left. Okay? This appears to be stars that are pretty hot. They're on the left, they're kind of bluish, but they're very non-luminous. They're not bright at all. These turn out to be stellar remnants, white dwarfs. This is what's left over after a star dies. And it's no longer fusing, it's no longer shining through fusion, it's just cooling off. It starts off very small and very hot, it just cools off, moves from hotter to cooler and cooler over billions of years. Okay, and as we'll see, there's more information even than this, all contained in this one plot. So we're going to go through today talking about all the different things you learned just by plotting stars on this chart. Are there any questions before? I'm going to spend a lot more time talking about this, but are there any questions so far? So I think one thing that's really might help, because this is kind of, this one plot, even though I'm really excited about it, it's a little dry. Here's a really nice video I want to show you, showing you take a star cluster, and it really illustrates really well how one of these diagrams is constructed from a star cluster. I'll move to this video by the European Space Agency. This is starting with a star cluster, Omega Centauri. And so all the stars in the star cluster are going to be made into an
This
HR
is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort the stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness, the brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot. But even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope,
So that illustration is really cool. Let me just show it one more time, kind of sped up. It really helps you see how the HR diagram is constructed.
this is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort the stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness, the brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot. But even that runs out. They end up burning out as white dwarfs.
Well, there's a tremendous amount of information in this HR diagram. We just started plotting the luminosity against the temperature of stars. You see all this interesting stuff. You see this is where their stars are burning hydrogen. This is where they're dying. As they mentioned, we're burning about in their death throes. They briefly start fusing helium even. And then these are the stellar remnants, the cores of dead stars. So there's a link to that video here if you want to check it out on your own. Okay, so one thing we want to understand about this diagram is how can we understand sort of what we see about the main sequence going from the upper left to the lower right? Why is that? And can we understand how that relates to the size of stars and the temperature of stars? So remember we talked about the Stefan-Boltzmann law. Okay, the luminosity of a star depends on its size and its temperature. And so if we want to compare, say, the luminosity of a star to the luminosity of the sun, is it twice as luminous? Is it 10 times as luminous? We need to know how big is it compared to the sun? So the ratio of its radius to the radius of the sun. And it depends on the square of that. Or we need to know the temperature. And we need to know the temperature of that star compared to the temperature of the sun. And the luminosity goes as the fourth power of that. So if the star is twice as large as the sun, then the luminosity is increased by a factor of 4. If the temperature of the star is twice that of the sun, the luminosity is increased by a factor of 16, 2 times 2 times 2 times 2. And so these are the two things that determine how luminous a star is: its temperature and its size. And remember, when we draw an HR diagram, we know its luminosity. That's one of the things we plot. We know its temperature. That's the other axis of what we plot. So we can actually derive what the size of a star is. So this begins for me to illustrate to you just how much information is contained in this HR diagram. We'll see that once you draw a point for a star on this HR diagram, you know its size too. And let me give you a sense for what these sizes are. So when we talk about stars on the main sequence, O-type stars, the bluer stars, are the largest. Here's the sun is a lot smaller than an O-type star. M-type stars are the smallest. Okay, so red stars, low temperature stars are very, very small. Blue stars, high temperature stars are very, very large. And as you can tell, both of those things cause a star to be more luminous. So an O-type star is both large, which increases its luminosity, and it has a high temperature, which also increases its luminosity. So what we expect then, and what we see, is that on an HR diagram, the bluer stars are way more luminous than the redder stars. And that's exactly what we see. Remember, if we go to the left in the diagram, and this is the main sequence, the bluer stars are way more luminous compared to the redder stars on the right. But not only that, not only can we learn about the main sequence, but as stars exit the main sequence, they turn into these red giants. Okay. As an example, here's our sun. It's like a little dot on the scale. Here's an example of a star that's entered its death throes, Arcturus. It's the same mass as our sun, but it's ballooned to about 30 times the size of our sun, and it's become redder. Okay. The key thing is though it's emitting more light because it's so much bigger. Here's a even more extreme example: a red supergiant. Well, just a supergiant because it's really big. It's several hundred times larger than the sun. Okay, so it's a massive star.
Got a doctor appointment today.
So
No.
this is
Go away.
the upper right hand of the diagram. Okay, this is the main sequence. You have smaller stars down here, bigger stars over here. But here you have stars that have moved from the main sequence to the upper right, meaning they're getting redder, they're moving to the right, and they're getting bigger. They're moving up. They're getting more luminous as they're getting redder. By the way, you see on this diagram down here, these are very, very small. For a given temperature, right? So say, think of this temperature here. For a given temperature, these are emitting way, way less light than stars on the main sequence. They must be really, really small. Okay, these are called white dwarfs. They're very, very small. Similarly, for a given temperature, if we look at, say, this temperature, like 4,000 degrees, a main sequence star is way less luminous than what's going on up here. These are red giants. And for a given temperature, they're much more luminous. That's because they're much larger. So on this diagram, if we want, we can put some more information. So here I've simplified the diagram a little bit by just showing a selected subsample of stars where I'm showing their size. Okay, so here's the main sequence. Here's the sun, and here I'm showing the size of stars. And you see along the main sequence, redder stars are smaller, bluer stars are larger. As we go to the upper right, you see that these giants, like red giants, for stars in their death throes, are very, very large. And you see that these white dwarfs in the lower left are very, very small. And using the Stefan-Boltzmann law, that fact that we know the luminosity, we know the temperature, we can calculate the size, we can draw these lines on the HR diagram, showing us what the size is for any star on the HR diagram in terms of the sun size. So what we see here is that if you move from the lower left to the upper right, you're increasing in size. Here, these examples of white dwarfs are less than 1/100th the size of the sun. Whereas once we get to these red giants and red supergiants, we're getting hundreds of times the size of the sun. So we started with just the luminosity and the temperature. We're starting to add more information that we can gather just by plotting stars on an HR diagram. I'll pause for a second, see if there's any questions so far.
Go your room.
So we can use the Stefan-Boltzmann
Go your room. Go your room.
luminosity, we know the temperature, we can figure out the star size. But it did also
Go your room. I'm in class, man.
what we can measure is the point of light. Okay, but we actually can check this.
I'm in class. Can you go your room?
You can visually see how big they are. So here's this picture just showing some examples. There's only a handful of examples of stars that are within 1,000 light years from us that are really, really big, like PHYS, Antares. I showed you Antares a second ago, and Betelgeuse, where we've actually directly imaged the surface of the star. It's a little blurry, but this is the best we could get. And you see these are kind of orange. These are red giants. Okay, so I do want to go through kind of one more time in more detail about how you construct an HR diagram, because it's so important to what we're talking about. So let's go through a sequence of slides where we remind you exactly what you need to do to make an HR diagram. So it's a graph where for each star, and you can do this for many, many stars, but for each star, you plot its position on the graph. Where you put it along the horizontal direction is dependent on its temperature. Okay, that can either be you can describe this temperature in terms of its actual temperature, like like 40,000, 30,000 degrees, 40,000 degrees for really blue stars, or 3,000 degrees for really red stars, or you can just give it the spectral type, right? So O, B, F, G, K, M. Okay. Here's the sun. It's a type G star. And where you place it in the vertical direction is its luminosity, right? Remember, we determine that from its apparent brightness and its distance. So typically, we have 1 representing the sun here, and here would be 10 times the luminosity of the sun, 100 times the luminosity of the sun, and so on, or 1/10 the luminosity of the sun, or 100th the luminosity of the sun, and so on. And then what we can do is we can do that same thing for many stars, right? So if we look at the night sky, we plot this diagram for many stars, it turns out not all stars are the same as the sun, okay? Some stars are bluer and more luminous and larger, right? So here, this is also showing their size. And some stars are redder, less luminous, smaller. And most stars are main sequence stars. So this line represents all stars that are fusing hydrogen into helium. That's the power source, right? We talk all about that when we talk about the stars.
Let's go to your room. Why are you in here again?
On this line, because this is where they spend most of their lives. Okay? But when they're active and producing energy, the period where they begin to die is very brief. But that does happen. Stars have a lifetime. Okay, we'll talk all about the lifetime of stars. At a certain point, they run out of hydrogen fuel. Okay, and they become more luminous but redder. So they tend to move a little bit to the right, so they get redder, but they go up. They get more luminous. They become giants or supergiants. That depends on their mass. We'll talk all about the life and death of stars later, and how, depending on their mass, they might just fuse hydrogen into helium, and then they might fuse helium. But if they're really massive, they'll start fusing carbon and heavier elements. And remember, this is actually where all the elements come from, right? This is where all the stuff, solid stuff, besides hydrogen and helium, that make up the human body, make up the Earth, that wouldn't be there if it weren't for the fact that some star a long, long time ago created that through fusion in its core. Okay, so you have stars getting redder and larger, lasts a small fraction of its life in death throes. Okay, and then finally they run out of fuel completely, and they crunch down, become very hot, but they don't have no fuel, so they cool off over time, and they're very small, so they're not luminous. They're called white dwarfs. So once they die, suddenly you find them being these very, very small, very white hot, small lights. They're called white dwarfs, and then cool off over time, moving to the right, getting less luminous, getting less. And then I can take that, start adding more information. Okay, so here's some of the more information we're going to talk about. Right, I mentioned size, radius. Right, so if you go from the lower left to the upper right of this diagram, the size of the stars are getting larger. And so we have these lines here representing the sizes of stars. Here's 1 sun size. There's 10 solar radii, so on. But we can also talk about how long stars live, their lifetimes, and their masses. And it's a little easier to clear away some of the the white dwarfs and the end of life stages of the stars, and just talk about the main sequence and how long stars live on the main sequence and how that's related to their mass. So this is something I want to talk about next. So look at all these stars fusing hydrogen to helium on the main sequence. It turns out that so here's 1 solar mass, the sun. When you move to the upper left, the stars are getting more and more massive. Okay? More massive stars burn hotter. They burn bluer, they're more luminous, they're larger. Less massive stars moving to the right, less redder stars moving down to the right, are less luminous, less massive. Okay? And it turns out that's related to their lifetime. The sun overall is going to last about 10 billion years before it runs out of hydrogen fuel. It's about halfway through that fuel source. So we've gone about 5 billion years. Another 5 billion years, the sun will be out of fuel. For stars that are more massive than the sun, they're so much more luminous that they actually, you might think that they'll last longer because they have more fuel because they're larger. But no, they burn so much hotter and are so much more luminous that they actually have shorter lifetimes. So I'll describe this in a moment. We understand this pretty well. But for example, stars that get towards like 100 times the mass of the sun, their whole life is only about 1 million years. So way, way shorter life than the sun. On the other hand, there's stars that are much smaller than the sun, maybe 1/10 the mass of the sun, whose lives will be 1 trillion years or more, way longer than the current age of the universe. Okay. Any questions so far about all of the stuff we can learn just once we plot a elliptical point on an HR diagram? So one thing I want to mention before going further is that when we classify a star, when we put it on an HR diagram, in the last lecture we talked all about spectral type, O, B, A, F, G, K, and M, representing the color or temperature of the surface of the star. We also talked about luminosity, but we didn't talk about a luminosity type or class in the same way, right? We didn't just put it into a category like O, B, A, F, G, K, M. Well, now is the time to do that. The reason why we waited is because it actually depends on the stage of life of a star. So here's a representation. Here's like a cartoon of an HR diagram. Here's a representation of what we call the luminosity classes, 0 through 7, okay, using Roman numerals. So there's a group 0 through 4, so that show up in the area in the upper right of an HR diagram, corresponding to the end of life stages of stars. That we call that are spectral class 0 through 4, but because they're for a given temperature, they're more luminous. So if we imagine some temperature, so think of a line like this, all of these are successively more and more luminous at that temperature. That's how they get their spectral class name. Most stars are spectral class 5, main sequence stars. Okay, so they show up here on this HR diagram. And then for a given temperature, there's stars that are less luminous than the main sequence stars, called subdwarfs and white dwarfs. So like the sun, for example, is classified G25. So the 2 represents like a sub-designation. So the sun is kind of halfway between F and G type. So it's G2. And then its luminosity class is 5. So G2, 5. Proxima Centauri, that really red, not luminous star, the closest star to us, Proxima Centauri, is also a main sequence star, luminosity class 5, but it's M5. So it's a very red, non-luminous star. Spectral class is M. Okay. One thing about HR diagrams is you get a whole lot of information, right, by only plotting really 2 numbers. Okay, it's luminosity and it's temperature. And we're talking about other things in addition to that. So here's just an example of a question. I'm going to go through it with you. You know, you observe a star and you want to plot it on an HR diagram. What do you need to measure? Do you need to measure its mass? We're going to talk about measuring masses in a minute. But no, you don't need to measure its mass. That's the one thing you don't need to measure. Okay? What you do need to measure is its spectral type, its temperature, and you need to know its luminosity, which means you need to know its distance and its apparent brightness. So if we go back to the nitty-gritty details of experiment, okay, you need to measure its distance, the apparent brightness. From that, you get its luminosity, and you need to get its spectral type in order to get its color. And then you can plot it on an HR diagram. And then you learn other things once you look at the HR diagram, like its size, its mass. We'll talk about lifetime, its stage of life. Okay, all these things you can learn just by looking at an HR diagram. But you only need to know to plot it its luminosity, and its temperature. Any questions before we move on to talking about how do we learn? How did we learn that masses of stars are related to their? Okay, so there's a really nice way of learning what a star's mass is. Okay? When we look out at the sky, there's a lot of stars that look close together. You know, constellations are an example, right? They look like the stars that are close together. Well, most stars and constellations are actually very far away. But when you see a couple stars that look close together, we call it a double star. And a double star could be two stars that actually are close together. That's called a binary star. And sometimes it's more than a binary star. Maybe it's 3 stars or 4 stars all orbiting each other, which you call that a multiple star system. Okay, but it could just be an optical double star, an optical multiple star system, meaning it just looks like they're close together, but they're actually very far apart. So here we're talking about stars that are actually orbiting each other, they're actually close together. We generally call those binary star systems, or if it's more than 2, a multiple star system. And it turns out that about half of all stars that we look up at the night sky, if we examine them closely, there's 2 or more stars orbiting each other. Happens to not be true for our sun. Our sun is just the one sun, right? But about half of all stars have a companion that they orbit around with. And when we watch their orbits, we can use Kepler's law to find out their mass. So this is very, very useful finding binary star systems. And there's a number of techniques that we can use to learn about the characteristics, the things we need to measure in order to determine the mass of stars from their orbits. And it depends on what we can see. So in the easiest case, for stars that are close to us, we can actually visually see the 2 stars. It's called a visual binary. Right? We can distinctly see them. We can maybe even watch over the course of months or years as they orbit each other. But that's kind of a special case because in a way, you only see one point of light. But luckily, there's 3 techniques that you can use. Sometimes we use more than one to nonetheless measure the fact that you have some unseen companion that's orbiting the other star. One is called the eclipsing technique. You imagine 2 stars, one comes in front or behind its companion and causes the star to flicker brighter or less bright as it passes in front or behind. Another method, that we'll talk about is spectroscopy. The stars, if they're orbiting, they're going closer to you and further away, closer, further away. And remember that causes a shift in the frequency of light. Okay, bluer as it's closer to you, redder as it moves further away. Bluer, redder. Okay, that's called Doppler shift. We'll talk about that. Finally, there's the possibility that you only see one star. Maybe its companion is not very bright, but that one star actually wobbles. So it's called astrometry. You watch that star wobble in response to the gravity of its unseen companion. And if you measure the period of that wobble, you learn the period of oscillation or of orbit of that binary star system. So all of these methods are used, and I'll explain how, to find stars in the sky. We plot them on an HR diagram, right? We see their luminosity, we see their temperature, and we can find their mass from their orbital characteristics. So let's first talk about some visual binaries. So let's go to Ursa Major. Let's go to the handle of the Big Dipper. So here's constellation of Big Dipper. And in the handle, there's a system called Mizar and Alcor. Now, for a long time, people thought this was a binary system, Mizar and Alcor, orbiting each other. So they thought it was a 2-star system. Okay, but actually it's a 6-star system. If we zoom in just on one of these two, Mizar, this is what we see. So Mizar, we can actually visually see that itself is a two-star system, or what looks like a two-star system, where we see one star here over about a month orbiting around its companion. And that's using the visual technique, because we can visually see this. But it turns out that if you look even closer using one of these other techniques, like a spectroscopy technique, you see that each of these are themselves two more stars. Okay? And it turns out that Alcor is also two more stars. So the star system, by the way, is so close that we can really clearly see the difference between Mizar here and Alcor here. But again, if we look really close, Alcor is itself two stars, and Mizar is two stars orbiting two other stars. So overall, it's a 6-star system. Here's another really famous example. This is the closest star system to us. Right, the star system is called Alpha Centauri, and right, when we say what's the closest star to us, we say Alpha Centauri. It's about 4 light years away, but that's actually a 3-star system, and you can see them. They're so close that you can really clearly see all 3. Here's Alpha Centauri, Beta Centauri, and the least easy to see one, Proxima Centauri, which is an M-type star. In other words, it's very red, very dim, and I've had to circle it because it's very hard to see. But again, this is a case where we can measure their orbits. We can see the distances between the stars. We can see how long it takes for them to orbit. We can see how fast they're moving. We can use Kepler's laws to figure out their masses, and we know where they are on an HR diagram, so we can therefore learn where a star is on an HR diagram once it's mass. Here's another visual binary. This one I just wanted to include because it's neat, because you can clearly see the 2 stars, and you can also clearly see that one of them is redder and one of them is bluer. One of them is much hotter than the other. And that's a result, because one of them is much bigger, much more massive. Another technique in cases that our stars are further away, so it allows us to extend this ability to find masses of stars to much further away, is the eclipsing binary technique. So here's an illustration where you have 2 stars. One could be bigger than the other one, or redder than the other one, or bluer than the other one. And so every, say, couple months, say this bluer star passes behind or in front of this redder star. And they have different sizes and different luminosities and different colors. And so when it takes the star, say, a day or so to pass in front of this star, you see either a dip or an increase in the brightness. You also see a change in the color. Okay, so every say month or couple months, you see a dip.
Just a little face of mask. Is it coming up?
Just a little differently the next month, because the other star passes in front. So it starts, it passes behind, and then it passes behind, and then in front. And in this way, we can very clearly determine the orbital period of these 2 stars. And we can also understand something about the speed, by how long it takes, how long this dip is, how long it takes one star to pass. So to make sure you're following along, let's do a quick interlude to a full question. This has to do with what we were just talking about. So suppose, hold up. Suppose you're just carefully measuring a star, right? This is your job. You're looking, you have this star that you're watching very carefully. And most of the time it has just a steady brightness, but every, say, 73 hours, the star becomes dimmer for 2 hours. There's an example of all sorts of different kinds of stars. But suppose this is what you see. Every set amount of time, it suddenly gets dimmer a little bit for a couple hours. And you just see this steady over and over and over again. What's the most likely explanation? 10 more seconds before I end the poll. Okay, I'm going to end it. And yeah, good. Most people got the correct answer. Right, this is an example of what you see when you see a star that's a member of an eclipsing binary. Okay, you see that you're just watching the star. It's just a point of light because that's all you can see. But that point of light is brighter or dimmer at a very fixed interval as one of the stars passes in front of the other. Okay, we'll talk about Cepheid variables later on. That's another type of stellar object. This is not a case of a star ejecting gas into space. There's no known objects, stellar objects that do that with such precise intervals, right? Every 72 hours. No, this is a good example of a binary star system.
Okay, so like, how do I get the gown?
But what?
How am I gonna get the gown?
I mean, how are you gonna get the gown?
Okay, another technique you can use when you just see a point of light, a star, but want to know its mass. Because if it's in a binary star system, you can learn that through the Doppler effect. Now remember, we talked about the Doppler effect. Maybe it's most familiar to you in terms of sound waves, because it's something through any kind of wave. So sound waves, like if you have a car that's coming towards you and then it drives by, you'll hear it. Right? It's the sound waves change
You need
frequency.
to wash the clothes away, you know?
The sound waves are getting bunched up, and so the frequency is higher. It's a higher pitch sound, and then when it passes you, the sound waves get stretched out, lower frequency sound. Okay. The same thing is true of light. Okay, when a source is moving towards you, the light waves get bunched up. They have a shorter wavelength. They're bluer. We call it blue shifted. Something's moving away from you, the waves are stretched out. We call those red shifted. So something will look redder. And recall that we can study that really precisely using spectral lines. So remember, if you take like a lamp with hydrogen in it and shine light through it, you'll get very specific absorption spectral lines, like shown here. That's characteristic of hydrogen, for example. And because those spectral lines are so precise, any movement, so if you have a star that's moving toward you, those spectral lines will all move to the right in that picture, all become bluer by the same amount. And when the star is moving away from you, all those spectral lines will be shifted to the red. They'll be indicating a red shift for the star is moving away from you. But not only are you seeing when the star is moving away from you and when the star is moving toward you, but you can actually precisely measure the velocity of the star. So you're learning not only the period, how long it takes the star to orbit the other star, we are also learning how fast it's orbiting, the actual velocity. This is incredibly useful because let me take a moment to describe how we actually measure the masses of these stars. We use a law that we talked all about previously, Kepler's law, which relates the period. So anytime you have two objects orbiting under gravity, there's a nice relationship between their period and their average orbital distance, A. So P stands for period here, A stands for their average orbital distance. The square of the period is related by a constant factor that depends on the masses of the objects to the cube of the average orbital distance. Okay. And since if you know the orbital period and the orbital distance, you also know the velocity. Those are related. So what that means is you only need to know 2 out of 3 things to measure the mass of the star. You either need to know the orbital period and the average orbital distance, or you need to know the orbital period and the orbital velocity, or you need to know the orbital separation and the orbital velocity. So either 2 out of the 3, orbital period, orbital separation, or orbital velocity, you need to know to calculate the mass of the star. And we can see from these examples that you can get that. In the visual case, you can see the orbital distance, you can see the orbital period. So that's enough to calculate the mass. For spectroscopy, right? You can see how long it takes it to go from blue shifted to red shifted to blue shifted, that's the period. And you can see how fast the star is moving, that's the velocity, and so on. Okay. So this is how we calculate the masses of stars and see the stars in the upper left of an HR diagram are very massive. Stars in the lower right are less massive. Now, another example, I'm not going to ask you this poll question, but right, just to make sure we're on the same page here. You know, how do you calculate the masses of stars in a binary star system? Well, there's a number of ways. One example is to know the orbital period and the average orbital distance. Okay. Now remember, some of these other options are things that are important, like D is, you know, you need to know the luminosity, or if you know the luminosity of the star and its distance from Earth, then you can calculate the apparent brightness. That was something we talked about. If you know the absolute magnitude and the luminosity, you can calculate the distance. That's something useful, okay? But that has nothing to do with a binary star system, right? You want to know a binary star system, you need to watch the orbit of that binary star system. You know the orbital period, how long it takes to orbit. You know the orbital distance and or the velocity of that orbit. Any questions before we talk a little bit about the range of stellar masses? So very, very massive. So what we find when we look at all these binary star systems is that we see a range of masses. The upper mass we see is about 150 solar masses. We never see stars more than about 150 times the mass of the sun. That's called the Eddington limit, right? We talked about the fact that if stars are too luminous, and remember, the more massive star, the more luminous it is. If it's too luminous, it literally will blow itself apart. And we'll see an example of that in a second, right? If a star is too massive, it has too much luminosity and it will blow itself apart. Low mass stars are much more common, but they have a limit. You don't see stars less than about 8% the mass of the sun, because then they're just basically big Jupiters. We call them brown dwarfs. They don't have enough mass to sustain fusion, so they can never enter the main sequence where you're generating energy through fusion of hydrogen. All right, so here's this cool example of our seeing a case where a star was a little bit above that 150 solar mass limit and was so unstable that it had kind of an enormous explosion in the 1840s, leaving this really awesome expanding nebula we call the homunculus nebula. And so remember in 1840 or so, there was a brief, the star that's actually really far away, 7,500 light years, briefly became the second brightest star in the sky as it shed about 30 times the mass of the sun in this explosion, so that it could go below that 150 solar mass limit and become more stable. So we can see now there's the star here that's about 1 million times as luminous as the sun. So this is that absolute upper limit of luminosities. Happens to be about 24 times the size. And on the other end, right, we have our familiar Alpha Centauri system. Alpha Centauri, Proxima Centauri on the right. Beta Centauri on the right. And Proxima Centauri, you can just barely make out inside this red circle. It's a very dim red star. And it's so dim because it's just about 1/10 of the mass of the sun. So it's a very, very low luminosity. So it's close to the lower limit in terms of how small a mass can be before it's not a star anymore. It's basically a big Jupiter. We call it brown dwarf. Okay, so how did astronomers discover the relationship between spectral type and mass in sequence stars? So remember, this has to do with, right, you plot an HR diagram. So you know its luminosity, you know the star's color, its temperature. But just by plotting something on an HR diagram, we now know the relationship between the spectral type of the star, right, where it is in temperature, and we know its mass. We don't have to figure it out anymore. We just know it. And we figured out that relationship by measuring the masses and spectral types of main sequence stars and binary star systems. See where it is on the HR diagram. Luckily, it's a binary star system, so we can measure its mass. Voila. Do that over and over and over again. You see very clearly more massive stars are bluer and brighter and follow exactly where we expect on the HR diagram. Now, there's this connection between mass and lifetime. So remember, you might think that a more massive star, say you think a star twice the mass, it's going to last twice as long, right? It's going to take twice as long to burn through all of its hydrogen fuel, but that's not true because, as we just talked about, more massive stars are much, much more luminous. In fact, they're way more luminous than you might expect. In fact, so maybe I'll just show this. You know, if you have a sun-like star and you say double its mass, it's like 16 times more luminous. So it's burning through its energy way faster than just twice the rate. Okay? And so this is sort of what you expect for sun-like stars. As you increase the mass, the luminosity goes way, way, way up. In general, so remember that high temperature, right? So more massive stars are bluer, and high temperature corresponds to more luminosity, right? It goes about proportional to temperature to the fourth power. That's why it goes up so fast. So they use up energy much, much more rapidly. Typically, the luminosity of a star scales as about mass to the fourth power. In other words, you double the mass, the luminosity increases by about a factor of 16. So using that, actually, we can do a calculation to figure out how long a given star will last. Well, let's use the fact that we know that our sun is going to last about 10 billion years. We did that calculation back when we talked about the sun a couple lectures ago. So the sun is going to last about 10 billion years. Well, if we take, say, a more massive star, okay, well, the first thing, if it has, say, twice as much fuel as the sun. So here I have, in general, any ratio of its mass to the sun's mass. So if I say twice the fuel of the sun, you might think it'll last twice as long. Okay, and that's what this factor here does. So okay, it'll last twice as long. But we also have to account for all the energy being lost, or how fast it's burning through all that fuel, which goes as the luminosity of that star compared to the sun. Well, if we plug in that the luminosity of that star goes as the fourth power of the mass, then we have this equation where we can cancel out like terms, and we end up with a calculation that shows that for a star, its lifetime is going to go as about 10 billion years. That's the lifetime of the sun, but it's going to be, I don't know why that won't highlight, it's going to be scaled by the mass of that star divided by the mass of the sun. In other words, how many times more massive is it than the sun? To the third power. Okay? In other words, if you increase a star's mass by just a factor of 2, its lifetime will be shortened by a factor of 8. And in this way, we learn that more massive stars become very, very short-lived. Okay? They're just burning through their fuel so quickly. Okay? And there'll be a consequence of this, which we'll see in the HR diagrams in a second. Here's an example, though, of 4-star main sequence stars. So they're all spectral class 5. That's what these V's are, Roman numeral 5. They're all main sequence stars, but they differ in mass. So the sun, for example, has a lifetime of about 10 billion years. But Proxima Centauri, which is about 1/10 the mass of the sun, is going to last about 1 trillion years. So it's going to way outlast us before it runs out of its fuel. Okay, Sirius, that's the brightest star in the sky, is about twice the mass of the sun. And even though it's only twice the mass of the sun, it's going to last about 1/10 as long before it runs out of its fuel, about 1 billion years. And here's a much larger, more massive star, an example of a really blue star called Upsilon Orionis, about 20 times the mass of the sun. It's only going to last about 10 million years. And there's even more massive stars. Remember, they can go up to about 150 solar masses. That case of Eta Carinae, let me go back. Eta Carinae is more than 100 solar masses. Its lifetime is only about 1 million years. And in fact, it's already about 1 million years old, so it could go supernova. That's something we'll talk about in the future. It could die in its ability to use hydrogen fuel, and then end up catastrophically dying in about possibly our lifetimes. Could happen. That would be really exciting. So let's do an overview of all the stellar properties for a moment before we move on, which is kind of cool. It's all the things that are tied together by an HR diagram. We talked about luminosity, okay? You learn that from, if you know the brightness of a star and the distance of the star, you get the luminosity. And this is what you plot, one of the axes on the HR diagram. And it ranges between about a 10,000th the luminosity of the sun up to about 1 millionth the luminosity of the sun. When we also look at a star, we can measure its color or its temperature or its spectral type, which goes from about 3,000 degrees up to about 50,000 degrees. Okay, and with just those two ingredients, we can make an HR diagram, where from that we can know the radius of the star. We also have cases that I showed you where we could actually see it, but just from that we can infer the radius. Main sequence stars radii go from about 1/10 the size of the sun to about 20 times the size of the sun. Once you exit the main sequence and go to those red giants, they could balloon to be about 1,000 times the size of the sun. We also learn the mass. When you look at a star on the HR diagram, you know its mass. We figured that out using binary star systems. And the mass of stars range from about 8% of the mass of the sun up to about 150 times the mass of the sun. Okay, and as we'll see very clearly in HR diagrams in a second, another thing we'll know just from looking at an HR diagram is the lifetime of a star. Okay, we know that just because of how quickly they're burning through their fuel from their luminosity. But we'll see a really cool illustration of that in a second. And we learn that stars' lifetimes are about 1 million years, up to about 1 trillion years. Finally, one more thing you see in the HR diagram is the stage of life of a star. If you see it's on the main sequence, you know it's burning hydrogen fuel. If it's in the upper right-hand corner, you know that it's in the end of life stage where it's running out of hydrogen fuel, possibly burning other elements like helium or carbon. And if you see it in the lower left, you know that it's a stellar remnant, it's a dead star. So HR diagrams are really, really cool. Now, let me do one more poll question for you, which is, I want you to think about this, right? We went through all of those characteristics. Let me get my poll ready. Went through all of those stellar characteristics. There's some that you plot. There's some, you use the luminosity and the color or the temperature to plot where the star is on the HR diagram. That's different from what determines, right? What determines where a star ends up on an HR diagram? What are the two fundamental things that really determine what its brightness is, what its luminosity is, what its temperature is that we talked about? Okay, I'll give you 10 more seconds. Okay, I'm going to end the poll. Okay, most people got the right answer, which is that, look, the thing that ultimately determines where a star is going to be on an HR diagram is mass. Right? So you start with some mass. And that determines everything except also just what is stage of life. Is it on the main sequence, or is it dying, or is it dead? So those are the two things that characterize how a star is going to end up on an HR diagram. But of course, what you measure on an HR diagram to put it there is just luminosity.
Mass and its stage of life. Okay.
And Any questions so far? So I have one more topic I want to cover in this lecture, which is a really cool thing we can see when we look at HR diagrams, is we can plot an HR diagram for specific groups of stars that all were born around the same time and that have similar characteristics. These are called clusters of stars. In general, we'll see that there's stars we call population 1 that are metal rich, because metals, we mean things heavier than hydrogen and helium that have been created in the cores of stars as they've lived and died and fused to create heavier elements. So if you have stars that are living and dying, they become metal rich. Future generations of stars have a few percent metals. That's called population 1. These are found in the disks of galaxies where there's lots of turnover, lots of new stars being created. But then you have kind of the dead area and the spheroidal part of galaxies, where you have lots of old stars that have been around so long that there hasn't been much stellar turnover. Okay, these are stars that they've only been a couple generations since the Big Bang, and so they're metal poor. They're mostly hydrogen and helium. Finally, there's population 3 stars that are metal free. These don't exist anymore. Okay, all the stars are gone that initially existed at the Big Bang that were only made of hydrogen and helium. Now all stars have little bits of metals because they're all second or third generation stars. And to study this sort of thing, we can look at star clusters. There's 2 main kinds of clusters. There's what we call open clusters, which are a group of just several thousand stars that tend to be in the disks of galaxies where there's lots of gas and dust and there's lots of stellar creation. And then there's globular clusters, which are these huge million clusters, clusters of millions of stars that tend to be out in the edges and what we call the halo of the galaxy. So there's a cross section of our galaxy. Here's the disk, lots of open clusters in the disk with younger, newer stars, and then globular clusters that tend to have older stars. And what's cool is we can make HR diagrams of specific clusters, where all the stars formed at the same time. Let me just show some pictures of clusters. Here's the famous open cluster that you can see in the night sky. It's kind of a blurry patch because it's a bunch of stars close together. And you see that there's gas and dust here. That's because there's stars being formed in this region from that gas and dust. So we call that a nebula. So nebula tend to be associated with open clusters.
Mhm.
Here's a dozen open clusters. Open clusters look very different from globular clusters, which are kind of spectacular because they're like a million stars. There's 2 examples of globular clusters. And what I'm trying to get to, though, is you can make an HR diagram of all the stars just in one specific cluster, all it formed around the same time. So what I want to get to a plot like this. So here's an example of one cluster that's about 100 million years old. And what you see is all these stars are on the main sequence, except there's no stars whose spectral types are O or B. Why might that be? Well, those are the stars that burn out fastest. So if all these, so you imagine a cluster forms, all the stars form at the same time. Some stars are less massive, some are more massive. Well, the more massive stars have died out. So you're left only with stars whose lifetimes are longer than about 100 million years. And you can see actually the ones whose lifetimes are about 100 million years old are in the process of dying. You're actually watching them expand into giants. So this is really amazing. And you can see this for all kinds of different clusters of stars. So here's HR diagrams plotted for 4 different clusters of different ages. Cluster H and Chi Persei, there's 2 clusters that are close together, whose are about 14 million years old, so very young. So basically, hardly any stars have yet died, but they're just in the process of dying. We have the Pleiades, about 100 million years old, where stars that are so massive that they would have died within 100 million years are already dead. Hyades, so there we see that cluster is about 650 million years old, because stars that aren't massive enough that they would have died off in 650 million years are all dead. And here's an example of a cluster that's about 7 billion years old. We call this the turn-off point. Okay, the turn-off point is the point indicating the age of the cluster where all the stars are beginning to die and turn into red giants. I have a little bit more I want to say about this, so I don't want to hurry myself too much. So I think this would be a good place to end. We'll come back next time to finish off this lecture, but give you a chance to, do you have any questions? All right, everyone, I'll see you next Monday. Have a good weekend. Thank you, Professor.
Thank you.
Thank you.